From powering cities to probing the cosmos, nuclear energy has emerged as a force to be reckoned with. At its heart lies a process called nuclear fission, a phenomenon that unleashes the tremendous energy bound within atoms. Imagine splitting an atom, not with a tiny scalpel, but by bombarding it with neutrons, subatomic particles with no charge. This collision creates a cascade of energy as the atom splits, releasing more neutrons in the process, leading to a self-sustaining chain reaction. This chain reaction is the engine of nuclear power plants around the world. The energy released, in the form of heat, is harnessed to produce steam. This steam drives turbines, which in turn power generators that ultimately deliver electricity to our homes and industries. It is a testament to human ingenuity, a way to harness the fundamental forces of the universe for our own needs. But as with any powerful technology, there's a catch. The process of nuclear fission, while remarkably efficient, produces byproducts. These byproducts, known as nuclear waste, present unique challenges that require careful management and attention. Understanding how this waste is produced is the first step in comprehending the complexities of nuclear energy and its impact on our world. Nuclear reactors, the heart of nuclear power plants, are marvels of engineering designed to control and harness the power of nuclear fission. Within these reactors, uranium fuel rods, enriched to enhance their fission potential, are carefully arranged. These rods are bombarded with neutrons, initiating a controlled chain reaction that generates an immense amount of heat. The heat produced is then absorbed by a coolant, often water, which circulates around the reactor core. This superheated coolant, now carrying the energy released from fission, is then used to produce steam. The steam, under high pressure, drives turbines connected to generators, ultimately producing electricity. As the uranium fuel undergoes fission, it doesn't simply disappear. Instead, it transforms. The original uranium atoms split into lighter elements, collectively known as fission products. These fission products are the heart of nuclear waste, containing a mixture of radioactive isotopes. These radioactive isotopes are unstable, emitting radiation as they decay over time in an attempt to reach a stable state. The type and intensity of radiation emitted vary depending on the specific isotope. Some isotopes decay quickly, posing a short-term radiation hazard, while others linger for centuries or even millennia, presenting long-term challenges for containment and storage. Section 4. Categorizing the leftovers. Nuclear waste is not a monolithic entity. It's categorized into three main types: low-level, intermediate-level, and high-level waste. This classification is based on the level of radioactivity and the associated risks. Understanding these categories is crucial for developing appropriate management strategies. Low-level waste, as the name suggests, has the lowest radioactivity. It includes items that have come into contact with radioactive materials, such as contaminated tools, protective clothing, and building materials. Intermediate-level waste sits in the middle ground, containing higher levels of radioactivity. Resins used in water treatment, reactor components, and some chemical sludges fall into this category. Finally, high-level waste, the most radioactive of the three, primarily consists of spent nuclear fuel. Section 5. Spent fuel and high-level waste. Spent nuclear fuel, the primary source of high-level waste, is what remains of the uranium fuel rods after they've spent several years inside a reactor. While no longer efficient enough to sustain the chain reaction required for power generation, these spent fuel rods are still highly radioactive. They contain a complex cocktail of fission products, some of which decay rapidly, while others persist for thousands of years. The management of spent nuclear fuel is one of the most significant challenges associated with nuclear power. These intensely radioactive materials require robust containment and isolation to prevent the release of harmful radiation into the environment. Section 6. Managing the nuclear legacy. The journey of nuclear waste doesn't end when it's removed from a reactor. The first stop for spent fuel is typically a spent fuel pool. These pools filled with water provide both cooling and shielding from the intense radiation emitted by the spent fuel assemblies. The water acts as a barrier, absorbing the radiation and dissipating the heat generated by the decay of radioactive isotopes. After spending several years in a spent fuel pool, the waste may be transferred to dry casks. These robust containers, typically made of steel and concrete, are designed for long-term storage. The thick walls of the casks provide shielding from radiation, while the internal design ensures the safe containment of the waste.